What's up, everybody? What day is tomorrow? Happy Wednesday. Happy shortened period day. Awesome. Okay, so today what we're going to do is we're just going to go over the last little bits of bonding and then wrap it all up. Yeah, so let me get started. Okay, so I want to kind of first talk about thermochemistry because this last little bit relates to thermochemistry. So you remember there's several things that you should know about thermochemistry. One is there's this thing called delta S, which is your entropy of the system. Entropy, if it's positive, that means it's getting more random. That means that it's dispersing matter more. And then delta G, that relates to, like spontaneity, whether something occurs. If it's negative, that means energy flows out the system. And that is good for, you know, understanding whether or not something happens. But the big one, the most common one, is delta H or enthalpy. And enthalpy is like the heat related to a system. Okay. So in this one, what you're going to have to do today is you're going to have to understand that um, the bonding, it takes energy to break bonds. And when you make bonds, it releases energy. And there's this like battle between the reactants and products. And that determines whether or not the delta H is negative or positive. So I'm just going to review a quick few of these things. This is good review as the AP test draws nigh. Okay, so first off, let's talk about when the surroundings get hot. So surroundings means that the system is releasing heat, so that's negative. Okay, so an uphill diagram, something like this, that would be positive, right? That's endothermic. Energy is a product, so oftentimes they'll write it like, oh, it's energy is released. So this would be negative, right? It's released. Delta H is positive. That would be positive as well. Um, so it'd be endothermic. Reactants have more energy. Okay, so if the reactants have more energy than the products, my reactants are here, my products are down here, right? Then that means it's going to release energy, and that energy released is going to be negative. This would be negative as well. Exothermic, downhill would be negative. Surroundings get cold would be positive. Products have more energy. This would be an uphill battle thing, so that would be positive. And then energy is a reaction that is positive as well. Okay, so that's just a quick little overview of some of the things with thermochemistry that we have talked about this year. Okay, let me move on to the next one. All right, now sometimes you'll see things like this, and I don't know if you remember this, but there's a name for it. It's called the Big Mama equation. It's the sum of all the products added up minus the sum of all the reactants, and that's equal to your delta H. It's equal to any state function, your delta S, your delta G, whatever. So what you have to do is, first thing, this is everything that they give you, right? So these are all the different things. So calculate the heat of combustion for pentane. So you're going to do like C5H12, right? Plus O2, arrow, CO2 plus H2O. That's combustion always, right? Then you have to balance it. So 5, 6. All right, let's see. I've got 10 plus 6. So I'm going to put an 8 here. All right. And then what you do from here is you take the sum of all of these minus these. All right. So let's do that real quick. So it would be 5 times negative 393. I'm just going to round for the sake of rounding. Plus 6 times negative 242. And this whole thing is going to be minus. And then do you see that this guy has a 1, and then oxygen is always 0. So it'll be minus a negative 173. So then we bust our calculator out. Let's bust it out. Oh, there we are. We're going to clear this out, and we're going to do 5 times a negative 393. It equals, make it negative, all right, plus 6 times, I think I did the order of operations wrong. Let me start over again. 5 times 393. I'm just going to make a negative at the end. Plus, let's do what kind of cheap calculator is this? Plus, where's my 6 times 242. Oh, geez. Well, you can just do simple math. My calculator is acting up, and I don't want to deal with it, but this should ring a bell. Okay. All right. So, anyways, So products minus reactants, it's the same thing for this one. So it's something you should understand. All right. And if you don't, you've got this. You can figure this out before May 6th. All right. Now, you have to kind of look at something and determine if bonds are being broken here. So in this case, do you see how this would be the ionization, or like this would actually be lattice enthalpy or lattice energy, that these guys right here, Ki, is broken apart into K plus and I minus. So this would definitely take energy. Okay. And when you go from a liquid, H2O liquid, to a gas, you have to break bonds to go, up. So this would also be positive. And then when you go from a solid to a liquid, this is also going to be positive. It's going to take energy. So anything that requires energy is positive. It's endothermic. Now, when energy is released when bonds are made, you see how these two come together. So this would automatically release energy. All right, we got this. Let's go. Okay. So then I want to mention this. So the heat of combustion. So there's another way to do this, and I'm going to kind of move me out of the way here so I can. I don't know if that's so the energy, the bond enthalpy, and that's what this little blank is. This is the bond enthalpy. So this is the energy needed to break the bonds and to put it all apart. So my delta H for this is the energy of all the bonds broken minus energy of all the bonds made. Okay, so everything on this side, this is all broken. You're broken. And these are all made. And so what you have to do in this unit, just like all the other units, is when in doubt, draw it out. So if they give you this, you have to individually draw each and every structure to know what the structure is. And then you have to count how much energy it takes to break each one of these bonds. And there's a chart. Let me show you this cool chart that tells you exactly how much energy for each of them. This is just found in your book. This is found in these notes. This is found everywhere. Okay, so to break a single bonded CH bond, it's 413 joules. I think it's kilojoules, actually. Yeah, it's kilojoules. And to break, look at this, to break an N triple bond is 945 kilojoules. Do you know why most of our atmosphere, here's nitrogen, right, with that triple bond, which, by the way, is one sigma bond and two pi bonds. You remember that? Okay, so anyways, this takes a lot of energy to break. So nitrogen kind of is pretty inert. They put it in our Lay's potato chips to keep them fresh, keep the oxygen out. Whereas a single bonded C bond is much easier to break. It's longer. It's a single bond. These long single bonds are easy to break. So, I mean, look at I. Whew, you can just breathe on it, it breaks. Okay, so we're going to kind of write a few numbers down here, and I'll come back to this in a second. So let me trash this. So we're definitely going to need 413. Ooh, messed that up. We're going to need 413. As soon as I write this, it's going to go down. Remember these. 413. We're going to need oxygen's double bond down here, 498, right there. We're going to need a CC bond, right? We're going to need all these bonds, all right? So let's go back. I'm going to go back here. See if I can go back finally. No, this is the worst presentation ever. Okay, so we're going to go back here, and you can see that I'm just going to kind of jot them down. Do you see how you need 1, 2, 3, 4, 5? So 5 times the CH bond. And then you're going to need 1 CC bond, because that's right here. And then you're going to need 1 CO bond. It's a single bond. And then um, one OH bond, right? And you add all these up. These are all going to be positive because they're on this bonds broken side. And then you're going to add to that 3 double bonds. 3 times your double bond, your OO double bond. And again, this is all positive on this side. I'm not going to be able to go back and forth. This is a problem with video lectures. I'm not very good at them. I'm sorry. Okay, but on this side, the product side over here, wow, look at this. Okay, these are all made bonds, and when they're made, they release energy, which is counterintuitive of AP Bio. If you were in that, they always talk about ADP, ATP. Trust me, if bonds are broken, it always takes energy to take stuff apart. Just think about taking apart all the kits, right? And if new bonds are made, it always releases energy. So now you're going to need, do you see how you have two double bonded CO bonds, right? You're going to need that times two. So there's going to be four total CO bonds. And then there's going to be two OH bonds, but there's three of them. So that's six total. So then this whole part is going to be negative. So then you go to this list over here. Let me trash this. Let's go to the next one. And you just add them up. You just look these up. And remember, we needed what, like five of these. So 5 times 4, 13. And then what do we have? A couple, we had where was a couple of these, right? We need some of those. We need this double bond. Look at that double bonded 804 right there. Whew. All right. So it's all the bonds on the left side are negative. Just add those up. All the bonds on the right side, swap that. All the bonds on the left side, the reactant side, are positive. That takes energy. All on the right are negative, and they release energy. And delta H is just the difference between bonds broken and bonds made. It's a novel way of looking at it. It's pretty cool. Okay, so just to show you, I'm going to do, I'll do this bottom one, which is super easy. Okay, so bonds broken, these are all positive on this part right here. And this is all negative. Okay, so C by itself, it's not bonded, so it's 0. So I'm going to do 0 plus, and I have one double bonded O. And you can see that's plus 498. Okay, so 0, I don't need that, plus 498, minus, and do you see how I have, I have to draw out the structure. It's two double bonds. You should just memorize that one. And so I have 2 times 804. So this is going to be 2 times 804. That's a times. And it's a negative 2 because bonds on the right are negative. So this is going to be minus 1608. And this is going to be plus 498. So you can see that the delta H is clearly going to be negative. And it's going to be like negative 1100. I'm going to estimate. You don't estimate. All right. You actually punch it in your calculator. All right, so remember, bonds broken, positive, right? Bonds made, negative. We got this. All right, now I'm going to clear this out, and I'm going to go on to the next thing. This is just another example. You just draw out the structures of each thing, and then you use the bond enthalpies they give you. I like it when they give you a nice, neat chart. They're like, hey, here's all the bonds you need. That's not always the case, but oftentimes they'll give you something like this. Okay, so I'm just going to move on, and I want to talk about localized versus delocalized. All right, so there's been some terms, and some people miss this on Pearson's, and I've seen this. So localized electrons, and you're going to talk about this when you talk about metallic bonding and resonance and all that. So they have an area. So like electrons in cyclohexane, look, they're here, right? And they are here, and they're in every point here. But what happens with this weird resonance structure? So delocalized electrons are found in resonance structures. And if you look at resonance, like this can have a double bond here, here, or here, or it can have alternating locations. This is benzene. And since it's benzene and since it has resonance, those double bonds can be in multiple locations. So the electrons are not confined to any one area between two atoms. They're free to move. And this gives them some interesting properties. And so that's kind of what they refer to as localized versus delocalized. Really, you just need to know delocalized are found in metallic and also in resonance structures. Okay, so this is just an example of the benzene delocalized electrons. So here's all the pi bonds. So pi bonds are like side by side bonds. So this is my pi bond here. And basically the electrons are like, sweet, I can go all over here and I can go over here. And that's what makes them delocalized, is all these electrons that are shared in the carbon bonds are actually free to roam within that specialized structure. So super cool. All right, now you may even run into some weird stuff with bond order. They'll sometimes, this is really not, you don't get into molecular orbital theory, which, if you go long enough, you'll get this. But what it is bond order basically is, if it's a single bond, you have a bond order of 1, right? If you're a double bond, you have a bond order of 2. And if you have a triple bond, you have a bond order of 3. Now, where is this weird? Well, let's look at this. Now, this is nitrate. So nitrate for sure has resonance. And resonance is when this double bond right here, it could be here, it could be here. And technically, you're supposed to draw each of the resonance structures out. That's what, by convention, what you do. But because this is delocalized, it's actually an average of all of those. It's actually a 1.33 bond. So that's the bond order of this. This would actually have this guy right here, since it's got resonance, would be a 1.5. So the bond order is either going to be 1, 2, 3, or 1.33 or 1.5. And you probably won't even see it, but I covered it. So there you go. Okay. All right. Now, I want to mention this because there was a lot of talk about people like not liking intermolecular forces. So here's what you have to do. You have to be able to look at something. I'm going to move me out of the way again. You have to be able to look at something and say, oh, the forces there are London dispersion or metallic bonding. And so, for example, if I have zinc, well, zinc isn't, it's a metal, so it's totally metallic bonding, right? So you look at it and you figure out, oh, it's got to be that. And that's super high properties because that's an intermolecular force. Oh, a diamond, you say. So they'll often put it like diamond, C diamond. Okay, diamond's like this, it's covalent network. It's like the strongest thing possible. So then they're going to ask you, like, all right, what forces are in CH4? And I can't say this enough. When in doubt, draw it out. So you draw it out and you find out that it's totally non-polar. And it has hydrogen in it, but it's no fun at all. And since it's no fun, it's not hydrogen bonding, it's not polar. This is London dispersion forces. Or if you want to call it this is van der Waals. Okay. Now let's look at this one. Do you see how the O is touching the H? Automatically, you got this. This is H bonding. Okay, so who wins? Who has higher strength? Well, does this London dispersion thing that's a gas, or does this liquid have it? See, that might be, let's see, 1, 2, 3, 4, 5, 6. That might be some sugar. That's a sugar, so that's a solid. Yeah, that's a sugar. Okay, look at this one. See how the O is touching the H? This has got hydrogen bonding. Now, is it true that both of these have London dispersion? Absolutely. Everything has London dispersion or van der Waals forces. But the predominant force is what they're looking for. The thing that gives us characteristic properties is H bonding. Okay, now this has O and this has H, but they're not touching, so this is dipole-dipole. Dipole squared. NaCl, it's not all nonmetals. It's a metal, nonmetal. This is ionic. Okay, so look at this guy. This is propane at the bottom. So you have to draw it out. And you find out it looks like this. It's just a bunch of nonpolarness. Okay, it's just a bunch of H's around. It's saturated. So this would be London. I know this isn't on your note sheet, but this is what kids sometimes mess around with and mess up. So just make sure you understand it. HF, that's so much fun. It's hydrogen bonding. Br2, well, the question is it polar? When you draw it, it looks like that. And it has a bunch of unshared pairs around it like this. So this is nonpolar, so that's London. This H2S. So you draw it and it looks like this. It's definitely bent. So that's polar. So that'd be dipole-dipole. This is so much fun. And this is polar, but it's not hydrogen bonding. So this is dipole-dipole. Okay, that's it for today. So today you'll do a couple things. You see the email, it tells you what to do. But fill out the notes, make sure this makes sense. And yeah, enjoy your late starts and go out to breakfast, live a little, and be well. I'm doing somewhat better, so hopefully I can be back. But it's been a rough couple days. All right, this is it.